जी तो अस्सलाम वालेकुम सब आ गए चलें जी लेट अस स्टार्ट बिस्मिल्लाहिर्रहमानिर्रहीम दिस इज आवर 15th lecture on BJT and previously we started with the BJT configurations and we did the first configuration in the last lecture, that was the common base configuration. This time we will start with the second configuration, and the title of the configuration is Common Emitter Configuration for the BJT. In the first slide, we will see the circuit diagram for common emitter configuration. Common emitter configuration is our second configuration, and it is the most frequently encountered transistor configuration, and it is shown in figure 3.12. The most frequently encountered transistor configuration appears in figure 3.12 for both PNP and NPN transistors. It is called common emitter configuration because the emitter terminal is common between both input and output terminals. That is, if we look at figure 3.12, we can see that in NPN case, in the first case, the emitter terminal is common between the base and the emitter and the collector and the emitter. In other words, we can say that in NPN case, the base current will eventually flow into the emitter and the collector current will also eventually flow into the emitter. Hence the emitter terminal for NPN case is common as shown. Then if we look at figure 3.12, figure part number B, we see PNP transistor with common emitter configuration. It is common because the emitter current is first, it is divided into the base current and the collector current. So in PNP case also, the total current flowing through the transistor, initially it flows through the emitter terminal. Hence the name common emitter. Now the two sets of characteristics that are essential to describe the behavior of common emitter configuration are input characteristics, or those characteristics between base and emitter, and the second characteristic is the output characteristic, or which is also called collector emitter characteristics. Now in this slide and the slide following, the current shown will be our conventional current. We will not discuss the operation of the transistor in terms of electronic current. In fact, we will discuss the operation of the transistor using conventional current. And the conventional current is the same as shown in diagram number 3.12. Diagram number 3.12 also shows the symbolic representation for transistor in common emitter configuration. First is the NPN case and second is the PNP transistor case. Now we come to the next slide. The next slide shows the characteristics, shows the two characteristics for common emitter configuration. Although the transistor configuration has changed, but the current relationship as those established in common base configuration are still applicable in common emitter configuration. That is, the emitter current in common emitter configuration is again the sum of collector current and the base current. That is, E is equal to IC plus IB. Emitter current is equal to the collector current plus base current. And secondly, the collector current is equal to beta times IB. That is, collector current is equal to the gain multiplied by the base current. And thirdly, the collector current is equal to alpha times IE. That is, the collector current is the product of the collector current can also be determined by the product of the alpha multiplied by the emitter current. Now, figures 3.13 part number B. Part number B, we will look at part number B first. The part number B shows the input characteristics. Here are the input characteristics. The input characteristics have been established between V base emitter on the x-axis and base current on the y-axis. We must not forget that the base emitter is a simple PN junction. Therefore, the characteristics will look very similar to those of a PN junction diode. And we can get a variety of characteristics by changing the voltage collector emitter. By changing the voltage collector emitter. Now our characteristics follow those characteristics of a PN junction. Here is the input characteristics. They resemble the PN junction diode characteristics. However, as we can change the emitter, as we can change the collector emitter voltage, therefore we can change the base current characteristics also by varying barrier potential base emitter. So in this diagram, as we change the base emitter voltage, as we change VBE from 0 volt up to 1 volt, how will the base current change? Initially, before we meet the barrier potential, that is before we meet 0.6 volt or 0.7 volt, the current will be essentially zero. No current will flow into the base up to the voltage 0.7. After the voltage, after we have increased base emitter voltage larger than 0.7, when we have broken the barrier potential, only then do we get an increase in the base current. Now this base current will have separate values for separate voltage of collector emitter. That is, for when VCE is 1 volt, that is in the first case when VCE is set to 1 volt. At that time, the base emitter, at that time the base collector, the base emitter current will flow. The base current will have a separate set of characteristics. And as we change the collector emitter voltage, then the base current will have a separate set of characteristics. Another important thing to note is that the base current is very small. Base current is in microampere. Now we come to figure 3.13, part number A. The part number A show the output characteristics. This is the output characteristics of common emitter configuration. It is a graph between voltage collector emitter on the x-axis, VCE on the x-axis, and the collector current on the y-axis. And we get a variety of characteristics by changing the value of base current. We change the value of base current. Now these characteristics are as per expected because collector current is equal to base is equal to beta times the base. So this means that as we go on increasing the base current, we increase the collector current also. So this is exactly what is happening. As base current is increasing, that is first 10 microampere, then 20 microampere, 30, 40, 50 up to 90 microampere, we observe increase in the collector characteristics also. And these characteristics have been divided into three regions. First is the cutoff region, which remains very close to the x-axis. Then is the saturation region, which remains very close to the y-axis. And then third is the active region. This active region is the region where we observe transistor amplification. And to use a transistor in and to use the transistor for amplification purposes, we must ensure that the transistor remains in the active region. However, since we can use a transistor in digital electronics also, while using a transistor in digital electronics, we must ensure that our transistor only works either in the cutoff region or in the saturation region. So if a transistor is being used for amplification, it must work only in active region. But if the transistor is being used for digital applications, where it will produce either logic 0 or 1, when a transistor is being used for digital application, we must ensure that the transistor works either in the saturation region or in the cutoff region. And another important thing to notice is that our base current is in microamperes, whereas the collector current is in milliamperes. The base current is in microamperes, whereas the collector current is in milliamperes. The reason is difference in collector characteristics can be shown through characteristic equations. That is, collector current is equal to alpha IE plus ICB, where ICB 0 means the current that flows from collector to when the base current is 0. And this will yield and explain the reason for different collector characteristics, where we see, for example, in this slide we see the collector current derivations, equation 3.8 and equation 3.9. And for linear amplification, cutoff for the common emitter configuration will be defined as by IC is equal to ICE 0. ICE 0 is the current that flows when the base current is 0. ICE 0 is this very small current which flows when the base current is very small. And if we look at the input characteristics can be modeled like that of the PN junction diode, where we take zero current up to 0.7 volt, and then after 0.7 volt the current becomes defined by the value of limiting resistor. Now the beta, again, for common emitter configuration, is the same. That is, beta is equal to the ratio of collector current and base current. That is, beta is equal to IC over IB. Now we can always establish a relationship between beta and alpha. To establish a relationship between beta and alpha, let us start from our well-known equation, that is the emitter current is equal to collector current plus base current. The base current in terms of collector current can be written as IC over IB, and the emitter current in terms of collector current can be written as IC over alpha. And we can take the collector current common, and we are left with 1 over alpha is equal to 1 plus 1 over beta. By rearranging, we get the equation 3.12 in terms of beta, that is, alpha is equal to beta over beta plus 1, or we can get equation 3.13 in terms of alpha, where beta is equal to alpha over 1 minus alpha. And we can establish that the ICE0 is equal to beta times ICB0. Another equation that we can establish is the relationship between emitter current and the base current. That is, emitter current is equal to bracket beta plus 1 into the base current. Now, how do we bias our common emitter? Biasing is the process of preparing our transistor for amplification. For the proper biasing of a common emitter amplifier, we must ensure that the base current flows as shown in figure 3.18 and the collector current flows in as shown in the same figure part number C. That is, we have to forward bias the base emitter and reverse bias the base collector. Now the fourth region is the breakdown region. It is the region where we will break down our transistor, and this breakdown region will eventually destroy or puncture through the transistor terminals. So we must always avoid the breakdown region. Right. After this, we come to the third and the final transistor configuration, which is called the common collector configuration. The common collector configuration, as the name suggests, is the configuration where the collector terminal common between base collector and emitter collector. And figure 3.20 demonstrate the common collector configuration for PNP case and NPN case. In the first diagram, we see PNP transistor with common collector connection. The collector is common between the base and the emitter. Likewise, in part number B, we see the NPN transistor for common. We see the NPN transistor for connected in common collector configuration, and the current shown show the conventional direction of current. The symbolic representation for common collector configuration for the BJT are also shown. However, this is a very rarely used configuration, and it is mostly used for impedance matching since it has a high input impedance and low output impedance.
Sir, what is impedance matching?
हाँ जी, हम इसी पे आते हैं अभी. Now, what is this term impedance matching? The term impedance matching means that we match or we relate the impedance as seen by the base to that seen by the emitter. Impedance matching is a term that relates two impedances which are related to each other, and they can be controlled by the fact that the collector current is equal to beta times the base current. In this diagram figure, in diagram figure number 3.21, we see common collector configuration used for impedance matching purpose. Now, in electronics, impedance matching is the practice of designing the input impedance of an electrical load or the output impedance of its corresponding signal source to maximize the power transfer or minimize signal reflection from the load. A source of electric power such as amplifier or for example radio transmitter has a source impedance. What is source impedance? The source impedance is the impedance present in the source, which is equivalent to an electrical resistance. An electric load such as a transmission line or antenna similarly has an impedance to its resistance. The maximum power theorem says that maximum power is transferred from the source to the load when the load resistance equals to the source resistance. If this condition then the two circuits are said that they have impedance has been matched so that we can transfer maximum power. This is the concept of impedance matching. And we can achieve impedance matching using a transistor in common collector configuration. Impedance matching
Yes,
can also be achieved using transformers, and in our case can also be achieved using transistors. Right, so up till now we have done the three configurations of the BJT, and in the next lecture um, I would like to solve a few examples for transistor in the three configurations. Okay. So if there is no other question, thank you very much for your time. So go through the theory and we will start with examples in our next lecture. Okay, thank you very much.
Sir, what is the course outline of this course?
I have distributed the course outline in my first lecture.
Okay, sir.
Can the CRs please respond that can the CR please respond?
सर मैं देखता हूँ. I'll send them.
हाँ जी यार देखें सबको भेजें. मैंने तो शुरू पहले लेक्चर में कोर्स आउटलाइन डिस्ट्रीब्यूट कर दिया था. तो इसकी जो थ्योरी है वो सब लाजमी पढ़े. All the students must go through the uh, literature of our textbooks. So thank you very much for your time. We will meet in a next class. Thank you.